Hello everyone and welcome back to tutorial 9 of MIE100, the tutorials course at the University of Toronto. This is Noor and I'm the video TA for the course, and I'm going to be still talking about the dynamics of rigid bodies, specifically plane kinetics of rigid bodies and impulse and momentum. I'm going to be doing 3 questions with you guys where we're going to be using the dynamics equations that we've learned before, and we're also going to be taking new material specifically about impulse and momentum. So stick through, and if you have any questions, as always, leave them in the comments below. Okay, so problem 1 tells us that given point C is moving to the right at a velocity of 0.5 meters per second, and linkage BD has an angular acceleration of 0.5 radians per second squared in the direction shown. Find the magnitude of acceleration of point B at the given instant. All right, so first of all, what do we know? We know that VC is 0.5 meters per second, and the angular acceleration of link BD is 0.5 radians per second squared. And we want to know the magnitude of acceleration at point B. So let's start with the free body diagram first. So let's take link BC. So here's our link. This is velocity VC. And VB is going to be pointing in the direction of link BA. And VBC, or the velocity of link B with respect to C, is going to be perpendicular to link BC. So this is 45 degrees, and this would also be 45 degrees. So after we've drawn the free body diagram, now we can use our relative velocity equations to know that VB, the velocity of B, is equal to the velocity of C plus the velocity of B with respect to C. And now we're going to convert that to angular motion relations. Which means that the velocity of B is equal to the velocity of C plus the angular velocity of BC, cross product, the radius of BC. Now, let's add up the velocities in the x direction. Okay. So we've got VB sine 30 is equal to 0.5 I, that's the value for VC, plus angular velocity BC cross product minus 1 I cosine, wait, let me write that so that I have more space, cross product minus 1 I cosine 45. So that's the distance, that's the length of BC. okay? Now, in the positive y direction, we've got VB cosine 30 is equal to VC is going to be 0 in the y direction, so we've only got VBC over here, which is going to be the angular velocity multiplied by the length in the j direction, sine 45. Okay, so VBC here is pointing upwards, that's why it's positive. However, it's pointing to the left, so that's why here it's negative. Okay, so let's solve these. So by solving these, we can get a value for the angular velocity of length BC, which is going to be 1.22 VB, which will then give us a value for VB, velocity at point B, which is 0.366 meters per second. And once we plug that into the angular velocity of BC, we get 0.45 radians per second. Okay, so we're just basically going to do simultaneous equations for those two equations over here. Equation 1, equation 2. Okay, now that we've got the angular velocity of BC, let's take a look at length DB over here. So we're going to draw another free body diagram. Here's our length. Okay. Here's the angular acceleration of length BD. And here's our velocity of point B at an angle of 30 degrees. Here it's also at an angle of 30 degrees. This is 30 degrees over here. And if you want to find the acceleration of B, it's going to split into two parts, tangential acceleration and the normal acceleration. So the normal acceleration is going to be perpendicular to the direction of the velocity, so it's going to be over here. And tangential acceleration is going to be in the same direction as the velocity, so it's going to be over here. Tangential acceleration. Now we can start solving again. So our relative motion equations is going to be VB is equal to VD plus VBD. However, because VD is a point and it doesn't move left or right or up or down, it's just a pivot, it's going to be equal to 0. So VB is just going to be equal to VBD, right? Now we're going to convert those to angular motions. So VB is going to be equal to the angular velocity of BD multiplied by the radius of BD. And since we already have the values for those, we can find the angular velocity of BD to be 0.366 radians per second. Now we can find the acceleration of B. So the acceleration of B is going to be equal to, again, AD plus ABD, and since VD is 0, so the acceleration is also 0. Therefore, the acceleration of B is just going to be equal to the acceleration of BD. Now we're going to split the acceleration into tangential and normal. So here we've got the tangential direction. And as we previously know, the tangential acceleration is equal to the angular acceleration multiplied by the radius of BD, okay, sine 30 in the I direction, because it's at an angle. So we want it to be in the positive x direction, plus the angular acceleration of BD, RBD, cosine 30 in the j direction. Because we also want it to be in the positive y direction. And now we're gonna plug in our known values. So we already know the angular acceleration of BD. So we're just gonna plug in 0.25I plus 0.433 J meters per second squared. And we're going to do the same thing for the normal. So we know that the normal acceleration is equal to the angular velocity squared multiplied by the radius, cosine 30 in the I direction, plus sine 30 in the j direction. And this here over here is negative because it's going to the right, and our positive is going up and to the right side. Sorry, this is going to the left. So our positive y and x are oriented over here. And since we, again, know all of the values, we can plug them into our equation to get minus 0.12 I plus 0.07 j meters per second squared. And since we want the magnitude of the acceleration, we're going to have to add up our normal and tangential equations. So we've got 0.25 minus 0.12 I plus 0.433 plus 0.07 j. And that's going to give us 0.13 I in the I direction and 0.5 in the j direction. And to finally find the magnitude of acceleration, we're going to have to put them under the square root. So 0.13 squared plus 0.5 squared. And that is going to finally give us 0.52 meters per second squared. Now for our second problem, it says here that each of the two uniform slender bars, OA and BC, has a mass of 8 kilograms. The bars are welded at A to form a T-shaped member and are rotating freely about a horizontal axis through O. If the bars have an angular velocity of 4 radians per second, as OA passes the horizontal position shown, calculate the total force R supported by the bearing at O. Okay, so what do we know in this question? We know that these are slender bars. Or something like thin rods. Okay. We also know that the mass for OA and the mass for BC are both 8 kilograms. And we know that the angular velocity at O is 4 radians per second. And we want to find the force R. So there's going to be some new material in this question to discuss. So we're going to start talking about plane motion equations. We know that the sum of forces is equal to mass times acceleration. So what is the sum of moments equal to? The sum of moments is going to be equal to the rotational inertia multiplied by the angular acceleration. So this is rotational inertia. Therefore, we know that the sum of moments at O, here in the bearing, is going to be equal to rotational inertia at O multiplied by the angular acceleration. This is the rotation of a rigid body about non-accelerating point O. It's a bearing, so it's non-accelerating, it's not moving, and this is the rotation of the rigid body around that point. Now, let's get back to our problem over here. We're going to draw a free body diagram. This is our rod OA, and this is BC. The weight of OA is going to be acting in the center. The weight of CB is also going to be acting here. At point O, we've got an angular velocity and a force acting on the bearing, RT, in the normal and in the tangential. Okay? Now, if you want to calculate the rotational inertia at around point O, you have to take a look at our diagram again. So for the rotational inertia for a slender bar or a thin rod that's rotating at only one end, such as OA, it's only rotating around the bearing here, the equation for that is 1 over 3 m squared. This part over here is for a thin rod rotating around one end. However, for the bar CB, it's rotating at the center, not at one end of the bar. So it's rotating over here. So the equation for that is 1 over 12 ml squared. This part over here is a thin rod rotating around the center. However, this is rotating around A, and we want to find the inertia around point O. So we're going to have to translate the inertia of A relative to O. So it's like we have to move that rod towards O. So the equation for that is going to be ml squared. And this equation over here is the inertia of point A relative to point O. And now that we've got our equation set up, now we can plug in our known values. So 1/3 multiplied by 8 multiplied by the length of OA, which is 0.5 squared, plus 1/12 multiplied by, again, 8 multiplied by 0.25 plus 0.25, which is 0.5. So that's the length of rod CB, plus 8 multiplied by 0.5 squared, to give us the rotational inertia is equal to 2.83 kilograms meters squared. Now, Newton's second law we know that the sum of moments around O is going to be equal to the force at OA multiplied by the distance from O to A, or from A to O, plus force at CB multiplied by the distance from B to C. So we're just gonna do our sum of moments around O over here. So mg, 8 multiplied by 9.81 multiplied by the distance, which is 0.25, and then for the rod CB, we've got 8 multiplied by 9.81 multiplied by also 0.5, because that's the length from O to A. Give us a sum of moments equal to 58.86 Newton meters. Now, if you recall back to our equation over here, sum of moments is equal to rotational inertia multiplied by the angular acceleration. If we plug in our sum of moments here, 58.86 into this equation, and our rotational inertia, which is 2.83, multiplied by the angular acceleration, we get an angular acceleration of 20.8 radians per second squared. Now, that's also not enough to find the forces. We still need to find RT and RN. So we're going to use our sum of forces now. Sum of forces in the t direction are equal to the sum of masses multiplied by the acceleration in the t direction. And the tangential acceleration is equal to, as we know, the angular acceleration multiplied by the radius, or the distance. So sum of forces in the t, we just have to look back at our free body diagram. So assuming that the positive direction is going down, we're going to get 2 masses minus RT, because RT is pointing upwards. And that's going to be equal to 8 multiplied by the angular acceleration multiplied by the distance to O, so from O to the middle of the rod is 0.25, plus rod CB from O to A is 0.5. And that's going to give us a value for RT, which is 32.2 newtons. That's the force pointing upwards on the bearing. Now for sum of forces in the normal direction, we know that the normal acceleration is equal to the angular velocity squared multiplied by the distance. So here we're going to take the positive x direction in this way. So Rn is going to be positive, and that's the only force in the x direction. So we're going to make it equal to 8 multiplied by 4 squared, the angular velocity, multiplied by the center of the rod, which is 0.25, plus 8 multiplied by 4 squared multiplied by 0.5 to give us a value for Rn, which is 96 newtons. Now, if we want to find the magnitude of the force, we're going to do tangential squared plus normal squared. And that is going to give us a value for R, which is equal to 101.3 newtons. Now for our last problem, number 3, we've got a uniform steel I-beam that has a mass of 300 kilograms and is supported in the vertical plane as shown. Determine the maximum angular velocity reached by the beam as it rotates in the vertical plane about the bearing at O. Also determine the corresponding force R supported by the pin at O for this condition. The mass of the bracket on the left end is so small and may be neglected. Also treat the beam as a uniform slender bar. So it's not we're not going to treat it as an I-beam, we're just going to treat it as a normal slender bar or a thin rod. Okay, so again, let's start with what we know. We know that this is just a slender bar or something like a thin rod for our rotational inertia. And what else do we know? We know that the mass of this bar is 300 kilograms. And that's about it. And we want to know the angular velocity around O, maximum angular velocity. And we also want to know the force applied at O. So first of all, we're going to start with our free body diagram. It's very important. Okay. So this is our bar over here. At the center, we've got the weight pointing down. We've also got our bearing O. So we've got the force RT pointing this way and normal force pointing that way. We've got our angular velocity. And this is the center of gravity. So since the angle over here is theta, and we know the angle over here is also theta. And if we connect point O to point G over here, we get an angle here. Let's call it, for example, beta. And the distance from O to G, let's call it R. Since this angle over here is beta, then this angle over here is also beta. And that's about it. Are we missing anything? Yeah, since the angle over here is theta and the angle over here is, since the angle over here is theta, we know that the angle over here is also going to be theta. And now we can start with our plane motion equations. We know that the sum of moments is going to be equal to the rotational inertia multiplied by the angular acceleration. And now we need to calculate the rotational acceleration. And since we're treating the system as just like a thin rod, and it's rotating around one end at the bearing at O, we know that it's going to be equal to 1/3 multiplied by MRAB squared. However, it's not like the bearing is right here at the center or at one end of the rod. It's actually a distance above the rod. Okay, so we need to calculate this distance over here. We know actually that this distance over here is 900 millimeters. Therefore, it's going to be plus MRAO squared. And since we already have all of these values, we can plug them into this equation. To get rotational inertia of 1,843 kilograms meters squared. Now, since we found the rotational inertia, let's try to also find R and beta. Okay, so beta is going to be equal to, here we've got like a little right angle triangle with beta in the middle. And we know the distance from O to A, which is 0.9 meters. And we also know the distance from A to G, which is 2 meters. So the angle beta is going to be equal to arctan 0.9 over 2, which gives us 24.2 degrees. And now since we found the angle beta, we can now easily also find distance r. So distance r is just going to be equal to 0.9 squared plus 2 squared under the square root. And this distance r is going to be equal to 2.19 meters. Now, it might not seem obvious why we're finding beta and r right now. However, we will be needing them to solve this problem. So let's get back to our sum of moments over here. So we know that the sum of moments is equal to force times distance, and the sum of moments around O is just going to be equal to the mass of the rod, 300, multiplied by 9.81. And the distance is going to be 2 cosine theta, because it's at an angle. And we want to find, so this is going to be our positive, So we want to find the distance from O to G, and that's going to be 2 cosine theta minus 0.9 sine theta, because if you look at the rod, if you look at our free body diagram over here, 2 cosine theta is actually the distance from A to G. However, we want the distance from G to O vertically. So that means there's this extra bit over here that we need to calculate for, right? This little distance over here is going to be 0.9 sine theta. Okay, so this is 2 cosine theta, and this little extra bit over here is 0.9 sine theta. And yeah, sorry, actually it's not an extra bit. Let me try to draw this diagram a little bit clearer, right? So here is our rod. Here's point O, here's point A, and this is point G. This over here is 2 cosine theta, but we actually want the distance directly underneath O from G to O. Okay, so this little distance over here is 0.9 sine theta. So we must subtract that from 2 cosine theta. That's going to give us the distance, the horizontal distance between O and G. 2 cosine theta minus 0.9 sine theta. I hope that made sense. Now, once we've plugged that in, we now know that 2,943, which is 300 multiplied by 9.81, multiplied by 2 cosine theta minus 0.9 sine theta is going to be equal to the rotational inertia, which is, we calculated, was 1,843 multiplied by the angular acceleration. And that's going to give us an angular acceleration of 1.597, 2 cosine theta minus 0.9 sine theta. Okay. Now, since we don't have the value for theta, we're gonna use another equation. We're gonna use the angular motion equation, one of the angular motion equations. We know that the angular velocity, the integral of the angular velocity integrated by the angular velocity is equal to the integral of the angular acceleration with respect to theta. So omega d omega is equal to alpha d theta. This is one of the angular motion equations. And we're going to use that in our problem to solve for the angular acceleration. So what's the integral of the angular acceleration? That's going to be omega squared over 2, and we're going to plug in our angular acceleration over here, so 1.597, and we're going to integrate our 2 cosine theta minus 0.9 sine theta. And that's going to give us omega squared is going to be equal to 3.19. And once we integrate 2 cosine theta from 0 to theta, we're going to get 2 sine theta, because 2 sine 0 is 0, minus 0.9, 1 minus cosine theta, because cosine 0 is 1. Now that we've got omega squared, we can then do d omega squared. We can then differentiate d omega squared with d theta. If we divide omega squared by d theta, this over here is the gradient or slope of omega squared, and at 0 it gives us the maximum or minimum angular velocity. Now this might sound a little bit complicated, but bear with me. Now we've got the gradient of a curve, because this is going to be, so omega squared is basically an equation of sine and cosine. So it's just going to be a sinusoidal curve. All right? And d omega squared over d theta is basically just the gradient, right? The gradient of the slope of the gradient of this sinusoidal wave. So if it's equal to 0, right, then it should be like a horizontal line. So it's either here or here or here or here. And those points over here on the graph are either the maximum or the minimum. And we want the maximum omega. And since the angular velocity is never going to be negative, or if it's negative, it's just going to be in the opposite direction. So that's the equation. Therefore, that's the equation we would need to find the maximum angular velocity. So again, d omega squared over d theta is going to be equal to 3.19, 2 cosine theta minus 0.9 sine theta. So we didn't integrate for that yet. And it's going to be equal to 0. So, So that means that for a maximum angular velocity, theta is going to be equal to arctan 2 over 0.9, because this is basically going to go to 0, and what's going to be left is 2 cosine theta is equal to 0.9 sine theta, and once you rearrange that, you get 2 over 9 tan theta, which then when you solve becomes arctan 2 over 0.9. So theta max is going to be 65.8 degrees, and therefore our maximum omega over here, omega squared, is going to be 3.19, and we're going to plug in our theta max. So sine 65 minus 0.91 minus cosine 65. And that's going to give us a value for the angular velocity, which is 2.03 radians per second. Now that's not the end of our question, right? We still got the force to calculate. Now we know that the sum of forces in the normal direction, let's say that this is the normal direction, because if we go back to our free body diagram over here, this is where Rn is pointed. So that's going to be equal to mr omega squared, right? Because the normal acceleration is equal to the angular velocity squared multiplied by the distance r. So sum of forces, we're just going to calculate it over here. It's going to be minus mg sine beta plus theta. And you need to always refer to your free body diagram to calculate those, right? So this is our mg, and this is our tangential and normal coordinates. So our normal is going to have to include both beta and theta. That's why we've got sine beta plus theta, plus Rn, because Rn is in the positive direction. And that's going to give us, if we plug in those values over here, minus 300 multiplied by 9.81 sine 24.2 plus 65.8 plus Rn. And once we calculate those, we can plug them into this equation over here to give us Rn minus 2,943 is equal to 300, and R over here is going to be the distance from G to O. And that's going to be equal to, as we calculated previously, 2.19 multiplied by 2.03 squared, the angular velocity we just found. And that's going to give us a value for the normal force equal to 5,650 newtons. Now, if we do the sum of forces in the tangential direction, we get mg cosine beta plus theta minus RT. Okay. Once we plug those in, this over here becomes 0 because the angle, the sum of those angles is equal to 90 degrees. So cosine 90 is equal to 0, which means that once we plug it into our equation, which is sum of forces is equal to m r angular acceleration. If we plug that in over here, we get minus RT minus RT is equal to 300 multiplied by 0, because the distance from G from A to O, from G to O, on the tangential plane, on the tangential axis, from G to O on the tangential axis is 0, because it's exactly on the normal axis. So since the distance in the R is going to be 0, RT is also going to be 0, right? Which means that the magnitude of our force, R, is just going to be equal to Rn, which is 5,650 newtons. That's the end of our problems. Thank you so much for watching this tutorial. I hope you learned something, and if you have any questions, as always, email me at noor.doidar@mail.ttoronto.ca or leave your question in the comments below. See you next week.